Solving general chemistry problems. Electrochemistry. We have learned how, in a voltaic or galvanic cell, oxidation occurs at the anode, which is therefore negatively charged with respect to the other electrode. Electrons flow from the anode to the cathode where reduction is occurring. Electrons are combining with cations on the surface of the cathode and depositing on it. This consumption of electrons is why it is positively charged. When we connect a voltmeter's negative terminal to the anode and positive terminal to the cathode, we read a positive voltage on the meter. If it is a Daniell cell under standard conditions, it reads plus 1.103 volts. The other kind of electrochemical cell is an electrolytic cell. While voltaic cells convert chemical energy into electrical energy and are a source of power like a battery, electrolytic cells take electrical energy and convert it into chemical energy. A source of power replaces the voltmeter and drives the electrons in the opposite direction. The electrode where reduction was previously occurring is now the site of oxidation. The cathode has turned into the anode. Recall that the name cathode is tied to the process of reduction. The two are synonyms. As well, oxidation and anode are tied to each other. However, when an external voltage source drives the reaction in reverse, the piece of metal which was the cathode now becomes the anode. One difference, however, is that in this case the external power source is pulling electrons out of the metal. The metal is still positively charged, but for different reasons. In the voltaic cell, it was positive because the chemical reaction of reduction was pulling electrons out of the metal. In the electrolytic case, it is the external power supply that is pulling electrons out. Similarly, the other electrode is now where reduction is occurring, and we can call it the cathode. However, it is negatively charged because the power supply is forcing electrons into the metal where, on the surface, they will react with aqueous ions to form the metal. In this piece of metal, either the reaction is driving in electrons or the power supply is. It is negatively charged in both situations. Electrolysis is a key industrial technology, and it is an essential component of almost all of modern life. Many metals are refined from their ores using either electrorefining or electrowinning processes. Electrorefining first forms an anode from the impure metal. In the electrolysis cell, the right voltage is applied, the desired metal is oxidized and dissolves in the solution, migrates to the cathode, where it is deposited in its purified form. The impure parts fall to the bottom of the cell. There is generally no salt bridge in an electrolysis cell. Electrowinning is close to the same, except the metal ores are dissolved in a solution. It's often acidic, but for instance, gold electrowinning is based on a cyanide. And then there's an inert anode, which is used to allow the metal to electroplate on the cathode. As you can see in these pictures, an electrorefining operation is enormous. The amount of electricity that is used to drive these reactions is huge. When a company builds an electrorefinery, they also build a hydroelectric plant nearby to supply the electricity. As an example, a copper electrowinning operation in Cerro Verde, Peru, operates 22,400 electrochemical cathodes that are each slightly larger than 1 square meter in area. The anodes are lead, but as you know, it's just there to deliver electrons. All the interesting chemistry happens at the cathode, where the copper ions in solution plate out on the cathodes. Each cathode stays in the plating solution for 6 days, and at the end it has acquired 130 kilograms of copper, and this is on each of the 22,400 cathodes. The electric current on each cathode is 400 amps. That's almost 9 million amps to run all of the cells simultaneously. For comparison, your home probably has an electrical panel that is rated for 160 amps. Now, a direct comparison is difficult, but the voltage in the electrorefining cell is quite small, perhaps 3 volts, while in your home it's 110 volts, at least in North America. So those 9 million amps at 3 volts could supply power for about 1,500 homes at 110 volts. The plant uses 2,189 kilowatt hours per ton of copper produced. Other industrial processes include electroplating, where a thin layer of a purified metal is deposited onto an object for durability, functionality, or aesthetic purposes. The chloralkali process electrolyzes a sodium chloride solution to form chlorine gas and sodium hydroxide, two important chemical precursors used throughout industry for various purposes. And this is just one of many such industrial processes. Another process of increasing importance into the future is production of hydrogen gas from water, which will be key for the future hydrogen economy and essential for clean energy. And a similar process can be used to produce oxygen gas, often for breathing, in submarines, for instance. Let's explore how an electrolysis cell is formed and operated. There is a single container of the electrolyte solution and two electrodes. In principle, no reaction is occurring. A DC power source is connected to the two electrodes, and the applied potential increases until a reaction begins to occur. An oxidation process happens at the anode and reduction at the cathode. The electrode to which the positive output terminal of the power supply is connected will behave as the cathode. Let's take a look at some typical problems. Consider a high-temperature electrolysis cell where the electrolyte consists of molten sodium chloride. If a sufficient potential is applied across the cell, what will form at the cathode? What will form at the anode? What's the minimum potential that must be applied? It is possible to melt inorganic salts, such as sodium chloride. Its melting point is 801 degrees Celsius. And then carry out electrolysis on that melt. The melt consists of free sodium ions and chloride ions. They're able to migrate freely through the melt. The first step in solving electrolysis problems like this is to completely identify all of the species present in the electrolyte. In this case, it is just sodium ions and chloride ions. Unless the problem specifies the nature of the electrodes, you can assume that non-reactive inert electrodes are being used. Next, look at a standard reduction potential table. Find all reactions which have these species as reactants. Something that is to be reduced will be on the reactant side of the equation in the table. However, something that is to be oxidized will be on the product side. We will envision the reverse reaction to be occurring. Now, you must have at least one possible reduction reaction and one possible oxidation process. Some reactions must be accepting electrons, and another process must be giving them up. In this case, we have these two processes, one for sodium and the other for chlorine. Now, you might see a problem here. We have provided the reactions for the aqueous ion species, but the reactions we are looking at are for ions in the melt, not in solution. In general chemistry, we tend to ignore the difference and just use the tabulated aqueous data, even for questions involving ions in melts. The data is just not readily available, and we can still examine the chemical principles we want to emphasize, so we will use the data as is. So look at these reactions. We use the sodium ion as a reactant, so the equation suggests we would form sodium metal by reduction at the cathode. The chlorine equation needs to be reversed in order to place the chloride as a reactant. The equation then is an oxidation, so we predict the chlorine gas will be formed at the anode. What is the required potential bias that must be applied? As before, the potential is found as cathode minus anode, which is minus 2.71 minus 1.36, or minus 4.07 volts. The negative voltage confirms that this reaction direction is not spontaneous. If we apply a voltage greater than this, we will be able to drive the reaction in the non-spontaneous direction and produce sodium metal and chlorine gas. Now, a word or two to remind you about the minus sign in determining the potential. The phrase cathode minus anode arises because the data we use is from standard reduction potentials. Another way of saying the same thing is cathode plus the negative of the anode. We take the SRP for the anode reaction from the table and change its sign because we want to use it as an oxidation. We add the two together to get the reaction's potential, and that gives the same answer in both ways. So we predict the minimum applied potential to be 407 volts. We say minimum applied potential because usually there are additional processes at work that will tend to require additional voltage to overcome. This is called overpotential. It always increases the minimum applied potential. If a question ever anticipates that you include an overpotential, it would need to state its value. You would always increase the applied potential from the minimum calculated from the SRP tables, but usually, to reinforce our general chemical understanding, we often neglect overpotential. The question will need to state it clearly if it is to be considered. Here is another question. This time consider the electrolysis cell to be filled with an aqueous solution of sodium chloride. What species form at each electrode and what potential should be applied? As before, start by identifying what species are present. We again have sodium ions and chloride ions, but in addition we also have lots of water. Now, how might that change the process? Look through the SRP tables for reactions involving water. You may find a lot of reactions involving water, but ensure that it doesn't call for other species that are not present in this process. Here are the reactions for chlorine and sodium. The tables provide valid data for these reactions as they are tabulated for the aqueous phase ions. We can also find these two reactions for water. One involves oxygen gas and the other hydrogen gas. These two reactions are very important. They must always be considered whenever you have an aqueous phase electrolyte solution. That means that for most general chemistry, you will probably have to consider these two reactions. Next, consider the two possible cathode reactions. These will be the ones which have one of the species that are present on the reactant side of the equation when it is written as a reduction. These will be the reduction of sodium and the reduction of water. The two possible anode reactions are the oxidation of chloride and the oxidation of water. Note how the oxidation of water at the anode will produce oxygen gas and H+, while the reduction of water at the cathode will produce hydrogen gas and hydroxide. Once the cell is connected, we start to increase the potential until a process begins to happen. We are looking for the pair of reactions, one reduction and one oxidation, that requires the smallest potential to be applied. We want to find the cathode reaction that is most positive or least negative. In this case, it is the reduction of water. Rather than forming sodium metal, water is reduced to produce hydrogen gas at the cathode. But an oxidation process must be occurring at the same time. The electrons have to come from somewhere. Now, if we use the cathode minus anode approach, then we are looking at their standard reduction potentials. We want the least negative overall cell potential, so we should be looking for the least positive or most negative number to subtract from the cathode. If, on the other hand, we were looking at these oxidation reactions and have, at least in our minds, switched the signs of the half reactions to be oxidations, then we would look for the most negative or least positive term. You will find different textbooks proposing the different approaches. If you understand why that minus sign is there, then you can use either one. In this case, the oxidation of water is less positive than for chloride, so we can predict that the oxidation of water to oxygen gas and the hydronium ion will occur first. The minimum applied potential would be minus 0.83, minus 1.23, or minus 2.06 volts. So an applied potential of just over 2 volts should produce hydrogen gas at the cathode and oxygen gas at the anode. In practice, however, the role of overvoltage comes into play. The overvoltage to produce oxygen gas can be as much as a volt. So in practice, we actually observe the production of chlorine gas at the anode. The sodium ion remains in solution and hydroxide ion is produced at the cathode. One starts to obtain a solution of sodium hydroxide. Meanwhile, one can collect the gas coming from the cathode. It is hydrogen and it can be sold. The cathode is producing chlorine gas, which can also be captured, stored, and sold. It's a very valuable chemical precursor for many things in industry. This is the chlor-alkali process. Chlor because of the chlorine, and alkali because of the alkaline nature of sodium hydroxide. The minimum potential will therefore be minus 0.83, minus 1.36, or minus 2.19 volts. Unless the question provides an overvoltage value for the water oxidation, you would give the previous answer. If a 1 volt overvoltage was part of the question, or if your instructor indicated earlier to always consider that value, then you would have to give the second answer. Let's review the approach to take with these questions. First, determine which species are present in the electrolyte. Are you dealing with an aqueous solution, or is it a melt of some ionic compound? If it is an aqueous solution, then be sure to consider both water reactions. Look at all of the cathode candidates. These reactions will have one of the species present show up as a reactant when the reaction is written as a reduction. The reaction with the least negative or most positive potential will occur first, meaning at a lower applied potential. Look at all of the anode candidates. These reactions will have one of the species present show up as a reactant when the reaction is written as an oxidation. The reaction will be the least positive or most negative potential, which will occur first. Check to see if the question specifies or if you are required to consider an overpotential. If so, make the reaction less favorable, cathode reaction more negative by that amount, or if an anode reaction, make its SRP more positive by that amount. Finally, the cell potential will be just cathode minus anode. Again, this assumes you are using the SRP values for the anode reaction still. Let's do one more example. Electrolyze an aqueous solution of K2SO4 using platinum electrodes. What will form at the anode? What is the product formed at the cathode? And what's the minimum potential needed to make this work? First of all, what is present? Well, we have potassium and sulfate ions with the water. We must consider the reductions of potassium and water at the cathode, and also the reduction of sulfate to either SO3 2- or SO2 needs to be considered. At the anode, the oxidation of water and the oxidation of sulfate must be considered. Sulfate can be oxidized to S2O8 2-. Given here are the relevant reactions with their standard reduction potentials. The first four are the potential cathode reactions, and the last two are potential anode reactions. The cathode will be controlled by the reaction with the most positive or least negative SRP. Now, this is the sulfate reduction to SO2. The anode is controlled by the reaction with the least positive or most negative SRP. In this case, it's the oxidation of water to give oxygen gas. So we will have O2 appearing at the anode and SO2 appearing at the cathode. The minimum required applied potential is 0.17 minus 1.23 or minus 1.06 volts. With no additional information about overpotentials, this is the answer to the question. There would be in practice some kind of overpotential for the water oxidation at least, maybe others. Things might change if they were considered, but not in the problem as we've been given it.